Alright, we're going to cover a few things out of Chapter 10. First thing is to identify Bronsted-Lowry acids and bases. And according to Bronsted-Lowry, an acid is a proton donor. So if I look at the first equation, here's HBr, and then I look at the other side and I just have Br minus. So that means this H was donated to the water. So in that case, this is the proton donor, which means it's the acid. The water is the proton acceptor, so it's the base. Then in our second reaction, I have water and HS minus. So if I look at the HS minus, over here it's H2S, which means this one took an H, so the water gave it an H. So this was the proton donor, so this is the acid, and HS would be the base since it accepted a proton. So here we can see in A, the HBr was the acid and that water was the base. And then in the second one, we can see that water was the acid and HS minus was the base. Okay, in our next one, we're supposed to identify conjugate acid-base pairs. So here I'm going to look at the HBr, and then I'm going to look and see what happened on the other side, and it's just Br minus, which means this one donated the H to the NH3. So since this is the proton donor, this is going to be my acid, which means this is the base. Now, what was left of the acid on the other side after it donated the H is called the conjugate base. So a conjugate base is after that acid donates an H, this is what I form. So it's always the acid formula and then you take off the H. Now in this case I have a base, and its conjugate pair is going to be one where it added an H. So here I have NH4+, and that is the conjugate acid. So one of the pairs is HBr and its conjugate base, so the acid and the conjugate base pair. The other one is this base with its conjugate acid. So a base becomes a conjugate acid, an acid becomes a conjugate base. And the conjugate base is when the acid loses an H, and the conjugate acid is formed when the base gains an H. Okay, in the next one I have to write the acid dissociation constant. So I have this equation, so there would be my equation, and in order to write my constant equation, that means I'm going to have to put products over reactants, just like I did before for equilibrium. So here I have my products over my reactants, and the water does not appear in there because water is a liquid, and just like in equilibrium expressions, I don't include liquids or solids. So it is exactly like writing an equilibrium constant expression. The only thing that's special is I put Ka here to show that it's an acid. Okay, my next one, I've been given the H3O plus concentration, and I want to find the OH minus. And we have an equation that says that if I take the H3O plus times the OH minus, I get 1 times 10 to the minus 14th. So I have the H plus, the 2 times 10 to the minus 3rd, and I have this. So I'm going to take the 1 times 10 to the minus 14th divided by my H3O plus, and that will tell me what my OH minus is. And since this has 2 significant figures, my answer is going to have 2 significant figures. And this is molarity, which is concentration, and that's what those brackets stand for, is concentration. The second part of this says, is the solution acidic, basic, or neutral? So I can tell by looking. So here's my H3O plus, it's 10 to the minus 3rd, and here's my OH minus, 10 to the negative 12. 2 times 10 to the negative 3rd is bigger than my 5 times 10 to the negative 12. And since my H3O plus concentration is greater than my OH minus concentration, that means that this is going to be acidic. If they are equal, then it's neutral. And if the OH minus is greater than the H3O plus, then it would be basic. Okay, in the next one, I have been given an H3O plus again, and they want me to find the pH. So in order to find pH, I have to do negative log of my H plus. So there's my equation, pH is negative log, and I plugged in my value for H3O plus. And since this has 2 significant figures, then I'm going to get 2 decimal places, because for logs my rules are the number of significant figures is my number of decimal places. And this pH of 2.77 indicates that that would be acidic. In my next one, I've been given OH minus, and I want to find pH. So this is going to take both parts from the last couple slides and put them together. So the first thing is I'm going to have to find the H+. So to do that, I take that 1 times 10 to the minus 14th and divide by my OH minus, because I'm using that equation from 2 slides ago, which was H plus times OH minus is the 1 times 10 to the minus 14th. So when I divide those, I get an H plus of 2.7 times 10 to the minus 12th. And then to find my pH, I do negative log of my H3O plus. So negative log of that H3O plus that I found. And since this has 2 significant figures, I'm going to get 2 decimal places. And this value of 11.57 indicates that it's a base. Okay, my next one, I'm going to go backwards. This time, I need to find the H3O plus, and they give me the pH. So to go backwards, in order to find H3O plus concentration, I do 10 to the negative pH. So 10 to the negative 8.25. And when I do on my calculator 10 to the negative 8.25, I get this number. And since this has 2 decimal places, I get 2 significant figures. So 5.6 times 10 to the minus 9th molar. And once again, those brackets means concentration, and that's molarity.